Okay, so I'm going to talk about, well, before I do, actually, let me congratulate Chi-Meow once again. Chi-Meow, you've been a force in our department ever since you've come, and in a good way. And this is, your award will turn you into a super Chi-Meow, and you're going to be able to get a heck of a lot done. I really appreciate you being here, been a great colleague. All right, so let us begin. So I'm going to be talking about quantum simulation of condensed matter models using cold atoms as stand-ins for the electrons. So the electrons are Fermi particles, and so we need periodic atoms to model the electrons in some kind of a lattice system. So the lattice is made optically using something we call an optical lattice. And as I'll show in a bit, there are various geometries of the optical lattice that one can adopt. So this has been a really golden era for quantum simulation with ultra-cold atoms. And I think it's only getting growing larger exponentially, actually. And there's a huge number of people now doing this from the perspective of AMO physics, where we know about interactions of atoms and light. So we're trying to address those kinds of technologies and methods using to direct towards many-body systems. So no, I'm not a condensed matter physicist. I just play one on TV. But I'm excited about the questions that we have. So so this gives why quantum simulation of ultra-cold atoms is interesting and productive. It's because the various parameters that define the system, things like dimensionality, density, temperature, the whole list of properties here on the left. I don't know if you can read in the back, but things like lattice parameters, spin polarization, spin orbit interaction, all of those things can be adjusted using cold atoms. And geometries that can also be adjusted. This is just showing the possibilities with a cubic optical lattice. If you have a one-dimensional standing wave, you can make an array of one-dimensional pancakes. If you have a two-dimensional optical lattice, a standing wave in two planar directions, produce out of the plane bundles of one-dimensional tubes. So one can easily study one-dimensional physics with that kind of geometry, as well as three-dimensional. And this is from a recent colloquium speaker, Peter Schaus, from the University of Virginia, and he's been making triangular optical lattices. So that has something to do with the kind of geometrical frustration that people were talking about earlier. And in particular, Meng and her talk. I think that it's possible to also make a Kagame lattice in the system. And so there's many things that one can do with this kind of a system, including quantum magnetism, and I'll talk about that very briefly. Exotic superconductivity, like the FFLO state, strongly interacting one-dimensional systems, quantum criticality, disordered insulators and topological materials, which is just a partial list. And the things with the arrows on them are things that I'm going to talk about right now. So in our experiments, we use lithium atoms, and historically, for me, that's because lithium comes in two stable isotopes, one of which is a fermion and one of which is a boson. In the fermion case, which is of interest here, lithium-6 is the composite fermion. It consists of an odd number of spin-and-a-half particles, and these are the various hyperfine sublevels in the ground state. So this is the only atomic physics I'm going to present in this talk. You don't have to worry. So this is it. These two lowest going states are generally our two spin states, and they're a pseudo spin. They're not obviously not real spin, but a pseudo spin. They're different in nuclear spin only and have the same electronic spin. So those two fermions in a gas can produce the ability to give us the ability to change the interaction of the function of magnetic field. And this is called a Feshbach resonance. It works by tuning magnetically at collisional resonance. And at the collisional resonance, the scattering length diverges to get in what's called the unitarity region. But down in here, where the scattering length's still large but modest, is a regime where we can study quantum magnetism and strongly correlated one-dimensional physics. All right, so the Hubbard model, this is the second time the hydrogen atom's been invoked, so maybe some of you want to be atomic physicists. So the hydrogen atom of condensed matter physics, I would say, is the Hubbard model. The Hubbard model is ubiquitous. We see it everywhere. It has two terms, one of which is kinetic energy and one of which is potential energy. The kinetic energy is given by the hopping from site to site. And U is the on-site interaction energy, which in this experiment is repulsive and tunable by Feshbach resonance. So that's the tunneling. That's the first term. That's a cartoon of the interaction. When there's a spin up and spin down atom on a site, they can interact repulsively, and that raises their energy. But we're dealing only with a single band model. And so there can only be, site can be unoccupied. It can have one electron per site, pseudo-electron, or two per site if they're of opposite spin. So this is really a paradigm model of strongly correlated matter. It's been proposed as a model for ITC superconductivity. We don't know. We don't know how ITC superconductivity actually works. And we don't know yet whether the Hubbard model is a valid model containing D-wave superconductivity. So this is a phase diagram of a yet unknown material. This is a hole doping along this axis. Actually, if you flip this over, there's particle doping on the other side. And then there's a few remarkable phases that exist here. There's antiferromagnetism. There's a pseudo-gap or strange metal phase. And there's a D-wave superconducting phase, presumably. And this is what we don't know. There's a perhaps quantum critical point here, but all of this in this very low temperature region is difficult to access for cold atom experiments, but also difficult to access for condensed matter physics as well because of impurities and defects and so on. All right, so this is cut right to the chase. This is the results of an experiment where we measure the static structure factor by doing light scattering. And we do the light scattering in such a way that the scattering is spin sensitive. And so we can do elastic scattering, which is very analogous to, say, neutron scattering. And there's experts in this room on that topic. Or X-ray scattering, but it's again spin sensitive. So this is the results of that experiment. This is a few years ago now. Static structure factor, which contains the correlations, the spin-spin, and the charge or density correlations as a function of interaction strength normalized to hopping. And you can see when U over T is about 10, that the structure factor hits a maximum. It's only 2, so it matters actually what this axis is over here in the y-axis, because this indicates that there are correlations developing, antiferromagnetic correlations that are developing to make it start to begin to look something like this. Well, it turns out that this data is above the Néel transition. We're actually above the transition for antiferromagnetic order, but just barely above it. We're essentially at that transition point. And you can see that there is then some development of a scattering structure factor. These are calculations from the highest temperature in the bottom here to the lowest temperature on the top. The lowest temperature is about 0.47 of T, of T star. And you can see that as a function of temperature that the correlations are developing rapidly. And the data fit one of these temperatures very well, which is this green one, which corresponds to about 0.51. You can see, by the sensitivity of the structure factor with temperature is extraordinary. I mean, this is just 10% from about 1 to about 0.5, so a factor of 2. All right, so our temperature fits a temperature which is relative to the Néel transition about 40% above it. So this was the first real direct measurement of antiferromagnetic order in these cold atom systems. But since then, people have done remarkable two-dimensional experiments where they are able to image directly single-site resolve images of the atoms in the lattice. And so with that, you're able to calculate all the correlations. And they're able to get to something like 0.4 of popping. So just right at the Néel transition, a little below it. So let me just acknowledge the people who did this experiment. It's been a while now, but Pedro Duarte and Russ Hart and Ernie Young and Xinxing Liu. And we've had a great group of theorists collaborating with us, from David Hughes, Nandini Trivedi, Richard Skulatar, Teresa Paiva, and Ehsan Katami. All right, so I'm going to move on now and talk about one-dimensional physics. So, which is something we're doing currently. So on the left, you can see the usual Landau Fermi liquid in 3 dimensions. Electrons are able to move around other electrons. The low energy excitations are fermionic quasi-particles. There's single particle life with some effective mass. But in the one-dimensional case, electrons can move to the right, they can move to the left, but they can't avoid each other. So an electron in one dimension on a one-dimensional wire is going to have some correlations with the adjacent particles. And so all the excitations are collective and they're sound-like, and they're therefore bosonic. And this is the foundations of the Tominaga-Luttinger liquid theory, in which there's some really profound predictions that we'll get to. So the difference in terms of the excitation spectrum is that in the Landau Fermi liquid theory, there's a continuum of energies for any momentum transfer up to from 0 to 2 times the Fermi momentum. In one dimension, on the other hand, there's not a Fermi surface, there are Fermi points. And the Fermi points are separated by twice the Fermi momentum. So we can have excitations that are about Q equals 0 or about Q is equal to 2kF, but they are all at low energy, they are all linear. And the linear means that they're sound-like waves, sound-like excitation. All right, this is the spin charge separation, which is a very strange but interesting effect. There are two kinds of excitations. There can be spin excitations, there can be density excitations. And it turns out that they move at different speeds. So this is showing two dispersion relations for the charge or the density, and in red the spin mode. So there have been a number of experiments in condensed matter looking at spin charge separation. Some of the first ones are shown here. This is from 1999 using nanotubes from rice from the Rick Smalley's lab. And this is something from Amir Yacobi's group from 2005 and Kim et al. In 2006. This is ARPES. This is a spin charge separation as a function of electron density. So this plot here showing the speeds, inverse speed, arise because of the change in the density of the electrons in these one-dimensional nanowires. So the issue in solid-state physics, if I may be so bold as to suggest that there's something imperfect about condensed matter physics with electrons, and that's that it's difficult to disentangle the Coulomb potential. The screening is important in these systems, and there are frequently defects and impurities and so on. And so it's been challenging in condensed matter physics to make a real quantitative comparison between data and theory, even though the theory of the model is essentially exact. So our colleague Guido Pagano, as a graduate student, used something called Bragg spectroscopy to measure the dynamical structure factor. So this includes energy and momentum, which are both obtained using this Bragg spectroscopy. But in their system, they were unable to resolve the spins because they're just nuclear spins. There's no Feshbach resonance in the atom they used. This is in Florence in 2014. But it was one of the first experiments to use Bragg spectroscopy with fermions in one dimension. And they were able to make a measurement, a very clean measurement of the structure factor. All right, then more recently, Emanuel Bloch's group in Munich used a deconfinement transition where they blew away an atom from this two-dimensional plane filled with spin up and spin down atoms. And that created excitations that they could monitor in real time. And they could see that the spin mode moved more slowly than the density mode. So they were able to see in a very nice qualitative way this observed fractionalization into spin-ons and holons. So this is experimentally how one can do such an experiment. This is, as I mentioned earlier, that there, if you use a two-dimensional optical lattice, you can produce a bundle of one-dimensional tubes, each of which in our experiment contains something like 50 to 100 atoms. So then we do Bragg spectroscopy as well. So we shine light at a particular angle and a particular wavelength, and that corresponds to a momentum transfer that's along this tube direction. And in our case, that momentum is about 20% of the Fermi momentum. So it's a very low energy. It's not zero energy, but it's a very low energy excitation. This is how one can separate the charge density wave from the spin density wave using the detuning of this Bragg the Bragg spectroscopy beams. So in this case, you can't, I didn't draw the detail, but there are two laser beams, almost like a Raman transition, except it's going to a different energy momentum state. All right, so this is what that looks like. This is a reference of the column density of the atoms we use to make a reference frame, and we subtract that reference from the case where there is a Bragg pulse. And you can see there's a little bit of a difference down in here. And that corresponds to a signal in which the red indicates a higher density. So atoms, after some time of flight, have accumulated some momentum from the Bragg spectroscopy, and they produce a Bragg signal that we can then plot. So it was worked out some time ago that this dynamic structure factor is related to the total amount of momentum, which is imparted to the gas. 5 minutes, right? So these are the structure factors for charge on the top and the spin modes on the bottom. The two in the middle should meet. They should be identical because one of them corresponds to spin, the other the charge, but they're at exactly the same non-interacting case, non-interacting scattering length, down to about 500 Bohr on the scattering length on the spin and 500 Bohr on the top for the charge. So the data, of course, are the symbols, but the solid lines indicate theory from Zhiwen Guan and Han Pu, in which the local density approximation is invoked because the density profile is not uniform. And this is using the beta ansatz with some adjustments for nonlinearity. And you can see the agreement's pretty good, but there are places where it's not. So down in here in the spin mode, yeah, down in this area, intermediate energy region, there's in the tail, there's not a perfect agreement. So this is a comparison. This is now a quantitative comparison with the theory. The theory is the dashed line. And there's only one free parameter, which is the temperature. That's 200 nanokelvin. And you can see that the data and the theory agree with each other very, very well. Now, and this really is, I think, the first quantitative measurement of spin charge separation. So this is that strongly interacting regime, and this is the non-interacting gas where there's no separation. So the nonlinearities turn out to be somewhat important if you want trying to make a quantitative measurement. The band curvature contributes, but it's difficult to accommodate in the theory for the spin mode. The backscattering is a significant correction, but it only applies, and that's illustrated here. It only applies to the spin mode. So, and I should really point out that the theory group made a heroic effort to account for backscattering. This is not a trivial calculation whatsoever. So, if you compare the linear and nonlinear models, you can see that the nonlinearities are in the solid line, and they're accounted for by the solid line, but not for the dashed line. That's just pure beta ansatz. So you can see it's particularly in the spin mode what the effect of the backscattering is. And I don't think, Han, correct me if I'm wrong, but I don't think it was really known that this backscattering was such a significant correction.
So why is it more significant for spin than for charge?
Because I can only hand wave the adjacent particles in the tube can be either spin aligned or anti-aligned. If they're anti-aligned, they'll interact via the contact interaction, which is weaker than if they're aligned and they're interacting via the essentially the Pauli principle. The Pauli principle is much stronger. And so the charge mode has, this is why it goes faster for the charge. Okay, so we also looked at the incoherence linear liquid recently, and this is if you increase the temperature of the system. This was worked out by Greg Feit, who's one of the few people that has really obtained results on this theoretically. And we can see this transition from a spin coherent to a spin incoherent to a completely thermal gas in these measurements. We're also doing P-wave, and I'm almost done. We're also doing P-wave experiments where we're trying to realize the Kitaev model that contains Majorana fermions in at the end of the wire. So this is the motivation for much of our work, is to be able to see this one-dimensional P-wave pairing. All right, so let me acknowledge people who did that second part. This is Ruin Senaratny. This is Ashish Kapla and Daniel Cavazos on the second to the end. All right, thank you.